Hello, welcome back to CS560 algorithms and their analysis. Okay, so today we will continue talking about the bottom-up dynamic programming solution for the matrix chain multiplication problem. Okay, so in our last video we talked about the optimal substructure of the problem. So basically, we can decompose the original problem of multiply a chain of matrices into subproblems. Okay, and the key operation, the key costs of solving subproblems is here the cost of multiplying two matrices together. Okay, so the optimal substructure can be described by this equation. So in order to solve the problem that starts from matrix, the I's matrix, and with the J's matrix, we need to find the K that minimize, K is between I and J, that minimize the total cost of the first subproblem that ranges from I to K, and the second subproblem that ranges from K plus 1 to J, and additional costs of multiplying the two resulting matrices together, which is Pi times Pk times Pj. Okay. And also we found that a recursive solution is very inefficient because we are solving the same problems over and over again if we implement this optimal substructure in a recursive way. Okay, so we must in the dynamic programming approach or solution, we need to make sure that we only solve each subproblem for only once, and when the second time we meet the same problem, we just use a lookup table or some similar mechanism to retrieve the old solution. Okay, so let's look at the bottom-up solution first. Okay, so speaking of bottom-up, we actually means that we need to solve the smallest subproblem. Okay, so in a matrix chain problem, the ultimate goal is to compute the multiplication between a chain of matrices, right? So among these, so within this long chain of matrices, we can find a bunch of subproblems, right? So what if so for example, if our original problem is A1 times A2 times A3 times A4 until AN. Okay. Say if we have n matrices to multiply together. So in order to solve the original problem, okay, we want to know how much scalar or how many scalar multiplication will be needed in order to compute this long chain. We basically need to solve all the distinct subproblems in this original problem. So for example, we need to solve A1, A2. Right. We also need to know what A3, A4 is. Right. We also need to know A minus 1 to AN as well. Okay. And also, we need to solve A1, A2, A3, and A2, A3, A4. an minus 2, n minus 1, and an. So we need to solve all these subproblems for once. Okay? So we say that the total number of distinct subproblem is this quantity. Okay, is what we call the combination of n over 2. So how do we come up with this quantity, this n over 2 quantity? Because each subproblem is, according to our paper here, one subproblem is defined by the starting index of the matrix, starting matrix index, and the ending matrix index. Okay, so this index 1 and 2 basically defines a subproblem, which is a1 times a2, and the index 3 and 4 defines a different subproblem. Okay, so we can use ai, aj to define the subproblem that we want to solve. Okay, just for so there could be numbers between I and j. So it could be ai dots to aj. Okay, so instead of writing a with subscript I and j, we can use I, j to indicate the distinct subproblem that starts from the i's matrix to the j's matrix. So for further simplification, we can use a 2D array to save the solutions to this subproblem. We can use the ith row and the j's column in the 2D array M to store the solution of solving the problem starting from matrix AI to matrix AJ. Okay. So that's and the quantity of n over 2 comes from a simple fact that in order to choose two different numbers combinations from n numbers, it is the combination of 2 over n numbers that you wanna choose. Okay. So all right, so now let's look at the next point. So that tells us one thing, that the subproblem, the size of subproblem ranges from 2 to n. Okay, so the smallest subproblem is has two matrices, and the largest subproblem has n matrices. And so we can think about a interesting question. So in order to solve all the subproblem of size 2, okay, you basically want to iterate over. You need to use a loop to iterate over all the subproblems of size 2, right? So in order to define a for loop, you need to know the starting index and the ending index. Okay, what are the ranges of I and j, right? Because the index I and j defines a subproblem. So in this case, if the subproblem, we limit the size of subproblems to 2, then what are the ranges of I and j, right? So this is something you can think of here. Let's go back to our paper. Okay, so now let's focus on the original problem of n matrices, the chain of n matrices. So in order to go over all the subproblems of size 2, right? So intuitively, you start from A1, A2, right? So the next one would be A2 and A3. A2 times A3, right? And the third one will be A3 times A4, and then A4 times A5. Okay, so if I write it on a different place, so let's say subproblems of size 2. So we can list it here. The first one is A1, A2, and the second one is A2 times A3, and the third one is A3 times A4, A4 times A5. So the last one, it's easy to imagine that it should be n minus 1 times an, right? So if you look at the indices, the starting index, the I, right? So I ranges from one to n minus 1, right? And what about j? So this is the index j. J ranges from 2 to n. Okay, so you can imagine this. Imagine there's a sliding window of size 2. Okay, so you can think of this black line as a sliding window of size 2 that slide from the left end of this chain towards the right end of the chain, and each time it moves by one matrix, right? So at the initial position, this sliding window covers A1 and A2, and after I move it one matrix to the right, it covers A2 and A3, and then A3 and A4, right? So that's why we have that the indices of I and J have such ranges. Okay, so this will be an important information in the implementation of our bottom-up solution to the problem. Okay, so the next one, let's look at a little bit bigger subproblem. Say, what about we are considering the subproblems of size 3, right? So it's a same way of thinking, and this way the only difference is that now we are considering a sliding window of size 3, right? So let's write this again. If we have A1, A2, A3, A4, A5 to an minus 2, an minus 1, and an. Okay. So if we want to solve all the subproblems of size 3, we will start with the initial position at A1 times A2 and A3, right? And the second subproblem of size 3 is A2, A3, and A4. And the third subproblem is A3 times A4 times A5, right? And so on. And the last problem will be A2 minus 1, AN minus 2 times AN minus 1 times AN. Okay? So that also tells us about the indices of I and J in the case of solving the subproblem of size 3. Okay? So it's easy to see that the index I ranges from 1 to n minus 2, and index J ranges from 3 to n. Okay. Okay. So this information basically tells that it's easy to implement a for loop that has a um, um, range defined so that the smallest subproblem solved before the bigger ones. Okay. So basically you can imagine a sliding window of size L when you want to solve all the subproblems of size L. Okay. And we will start from the smallest subproblem. So we will solve all the subproblems of size 2 first. And then we solve all the subproblems of size 3, and then 4 and 5 until we solve the last subproblem of size n minus 1. Okay. So let's just look at the pseudocode of this matrix chain procedure. Okay, so now when we look at this procedure, the matrix chain order procedure takes a array P as input. So in this P array, it actually stores all the dimension information for the n matrices. Okay, so you can think of the inputs as a array that has elements from P0 to P1 to Pn. Okay, so the P0 and P1 is the dimension of the first matrix A1, and so on. So for An, its dimension is stored in Pn-1 and Pn. Okay. And in the second line, we basically initialize two matrices or two arrays. Okay, so the M array that has n columns and n rows and n columns. So the two indices here, it ranges from 1 to n. And the S array, the 2D array S. So these two tables will be used to store the solutions to the subproblems. So why we are using two matrices, the two tables rather than just n? So here, because we not just need the optimal cost for the subproblem. So for the cost, it's stored in the 2D array n, but we also need to know how we obtain the optimal cost, right? So for example, when you solve the subproblem, when you solve the subproblem of from AI to AJ, right? I and J are the indices. So when you return the solution, we not only want to know how many scalar number multiplications we needed, but also we need to know where do we do the split, right? So when we solve the AI to AJ chain matrix problem, we are basically want to know the K, right? K is between I and J, so we want to know the K that give us the optimal solution, right? We want to see that AI to AK times AK plus 1 to AJ. And these splits will give us the optimal solution to this subproblem. Okay? So we not only need the total cost, but also the K. So the index K, the split index K, will be stored in the S matrices. Okay? And the cost will be stored in the M matrices. So that's why we need two 2D arrays. Okay, so now let's look at the main body of this procedure. So we actually, okay, so from line 3 to line 4, it's another initialization. Okay, it ranges 1 to n, and they make all elements, all the diagonal elements at the ith row and ith column to be 0. So this is also straightforward because MII is the result of the multiplying the chain of length 1. Right? So if the subproblem starts from I and ends with I, it's basically just one matrix. And so there's no need to solve it. So the number of scalar multiplications is 0 for all the cases here. Okay? So the actual work is done from line 5 to line 13. So look at the body of it. It's what we have been come across before. So it's like a 3 nested for loops, 3-layer for loops, right? So the first layer, the outer layer, the counter is L. Okay, the L ranges from 2 to n. Okay, so the L here, the comment says is the chain length. So L is actually the size of the subproblems. Okay, so that makes sense why it ranges from 2 to n, because we want to solve the smallest subproblem first. So this for loop from 2 to n makes sure that we solve all the subproblem of size 2 first. And after they are done, we solve size 3, and then 4, and then 2n. Okay, so L indicate the size of the subproblem. Okay, and there is a second layer for loop. It ranges from 1, right? It ranges from 1 to the ending quantity is n minus L plus 1. Okay, so this might be a little bit not that straightforward, but you can add a parenthesis here. You can think of n minus L plus 1 as n minus parenthesis L minus 1 parenthesis. Okay, you can put the L minus 1 into the brackets. So that defines the range of the starting index of the subproblem. Okay, so if we think of the case of subproblems, all subproblems of size 2, which means L is 2, then this quantity n minus 2 plus 1 equals n minus 1, right? So in that case, I ranges from 1 to n minus 1, which is the range of all the subproblems of size 2, right? We have shown this in the previous slide. We have shown that if we want to go through all subproblems of size 2, we need to go through A1 times A2, A2 times A3, and to A minus 1 times AN. So the starting index I starts from 1 to n minus 1. Okay, so here the quantity n minus L plus 1 is just a more general definition of the starting index of the subproblems. Okay, so according to 1i, we can define a j, right? We know that once we know the starting index of I, and we also know that the subproblem that we are solving now is size L, right? So the ending matrix, the ending index is naturally I plus L minus 1, right? So only by this J we can find the subproblem that, or we can identify the subproblem that starts with index I and has size L. Okay, so this J is defined here. So at line 8, we initialize the value in Mij to be infinity, right? That's for the convenience of later comparison in this third layer for loop. Okay, so the problem now becomes we by defining I and J, we can identify or locate where the subproblem is, and now the task is to solve that subproblem. Okay, so how do we solve it? Then we need to refer to the optimal substructure of this problem. In order to solve the subproblem that ranges from I to J, we need to split the subproblem by using some K, and we want to find the minimal combinations of the two parts of the subproblems, right? So that's what the third for loop from line 9 to line 13 does. So from line 9 here, we define a third loop counter K that starts from the I to J minus 1, right? Because let me open up this camera again, because this is what I wrote before. So in order to solve the subproblem of AI and J, we need to choose the K that gives us the smallest number of scalar multiplications. So this K splits AI to AJ, right? So K must be between I and J and be strictly smaller than J. So that's why at line 8, actually in line 9, we have a K, the loop counter K starts from I to J minus 1. Okay, and within the third loop body, this is a typical way of dynamic programming. So we look up the solution of solving the first part of the subproblem, which ranges from I to K. And we also look up the solution of, so here we use N, I, K to refer to the solution of this subproblem. AI to AK. And the second subproblem is MK minus plus 1 to AJ of optimally multiplying the subchain here from AK plus 1 to AJ. And the additional cost of multiplying the two resulting matrices is Pi minus 1 times Pk times Pj. Okay. So we let Q to be the summation of all these three parts, we let them to be Q. Right? And then we compare the Q with the original with the Mij, which is initialized by infinity, right? So if Q is smaller than that number, then we will replace the Mij with Q, and then we also store K into the S array. Okay, so in the next K, if the Q is smaller than the previous Q, we will overwrite the values in Mij and Sij. Okay, so this mechanism basically makes sure that we find the K that gives us the smallest Q, right? So the smallest Q finally will be the solution, will be the optimal solution to the subproblem from I to J, and the K is stored in Sij. Okay, so this is basically how the bottom-up algorithm works. Okay, so the subproblem of I to J is solved by the third for loop using the K loop counter, and the second for loop for I from 1 to n minus L plus 1, it basically goes over all possible subproblems that has a particular size L. And the outer for loop goes over all possible sizes for subproblems. And we must solve the smallest subproblem first, okay? Because the bigger ones relies on the smaller ones. Okay? And in terms of running time, it's easy to see that because we have 3-layer for loop, then the running time is bounded by a n cube. So, but it's not a super fast algorithm, but it's already way more efficient than the exponential time method, which is the brute force way that we first introduced in the previous video. Okay, so from the next slides, we will go through some simple examples of running this algorithm. All right, so now let's go through a simple example of running the matrix chain order procedure. Okay, so we consider a pretty short input chain that has 4 matrices from A1 to A2, A1 times A2 times A3 and times A4. So therefore, the input P parameter should have 5 elements, in which we've got P0 is 30, P1 is 35, P2 is 15, P3 is 5, and P4 is 10. So these are the numbers that define the dimensions of the corresponding matrix. So here we have matrix 1 is 30 by 35, matrix 2 is 35 by 15, and so on. Okay, so also we initialize the array M array and the S array in such a way. Okay, so let me just show M first. So M is a 4 by 4 array, but because we only use half of the elements in it, so we are showing this kind of diagonal part of this 2D array. Okay, and it turns out this is quite useful way of doing the calculation, and because from the line 3 to 4 code in the previous slide, we initialize the diagonal matrix diagonal elements to 0. Right, so that's why we have zeros at the bottom elements. So this one is M11, and this 0 corresponds to M22, and M33 and M44. Okay, so what the procedure does is to solve the smallest subproblem, which is of size 2 first. Okay, so in this original problem, we have 3 unique subproblems of size 2. The first one is A1 times A2, right? The second one is A2 times A3. And the third one is A3 times A4. Okay? And because we only have 2 for size 2 subproblem, there's actually we're not really solving it, because we're just computing the number of scalar multiplications needed in order to compute to multiply 2 matrices together. There's no other ways to do the parenthesization, right? We just times, so given the dimensions of A1 and A2, A1 is 30 times 35 and A2 is 35 times 15, so that's why the additional, the cost, or the number of scalar multiplications needed is 30 times 35 times 15. So we should put this value into M12, and M12 is this cell. Okay, so let's first solve M12, which gives us 15K750. Okay, and also the procedure will return the K. We also store the K in S12. Okay, so in the case of solving A1 times A2, in this case K is 1, because we should do the split here. Right, this is the only position to split A1 times A2. So that's why we put S12, put K into S12, which is 1. Okay, so S12 is stored here in the S array. Okay, and in the same way, we should solve A2 times A3. So because A2 is 35 times 15 and A3 is 15 times 5, so M23 is 2625, and S23 is 2. And similarly for M23 and S23. So we should copy these numbers into the M array, and we already did so for the S array. Okay, so now we have solved all subproblems of size 2. So this is a quite easy way, quite easy steps, because there's only just one K for for each subproblem, right? For subproblem A1 times A2, the K is 1, and for subproblem A2 times A3, the K is 2. For subproblem A3 times A4, K is 3, because there's no other options of a different Ks. Okay? So that's the first, the very first iteration for the most outer for loop. So now we're gonna solve the subproblems of size 3. Okay, so in this case we need to solve actually 2 subproblems. The first one is A1 times A2 times A3. Okay, so this is a bit different now. So because there are 2 ways of splits this subproblem. Okay, we can either do Option 1, we can either do A1 times A2 and A3. So we put the parentheses around 2 and 3, which means our K is 1. We do the splits at here, at this position. Or we could do this parenthesization. So we can let K equals 2, and what we are doing is let A times A2 first, and times A3. So K is 2. So these two options will result in different number of scalar multiplications needed. Okay, so let's go to the option 1. So in this case, the total cost of this split is the cost of the first subproblem, which is just A1. So let's say M1, 1. So according to the our pre-computation here, A11 is really 0 because it's just one matrix. It's really 0. Okay, and the total cost should be plus the second subproblem, which is M2, 3. Right, and M23, according to our computation, M23 is here is 2006.25. Okay, so here this is really where the dynamic programming part happens, because we refer to the table for the solution to a subproblem that we have solved in the previous iteration. So M23 is the solution to a subproblem of size 2, which we have been already solved in the previous slide, right? So we just look at the table and retrieve that value, and we need to plus the additional cost of the multiplying the two matrices, resulting two matrices together. So which is P0 and P1, right? And P3. Okay. So according to the table, we should have that so these information are available from the input parameter P. So we can have the solution like this. And for K equals 2, we need to first know what M12 is. So according to the table, M12 is 15,750, and plus M33, which is 0, and plus P0 and P2 times P3. Okay. So once we know the cost for K equals 1 and K equals 2, we just compare which one has smaller cost, and we will store the smaller cost to the matrix which we need to choose the minimum values among these two options, and store the cost to N13, and also store the K to S13. Okay. So having these numbers computed, right, we can see that this one is 7,875, which is smaller than 17,100. So of course we will choose this one as the optimal solution to M13, and K should be 1. Okay. So that's why we update our table by copy the 7,875 into here, and K equals 1 into this cell in the S area. Okay, and now we do the same thing for solving the second subproblem. The second subproblem is, so the second subproblem is A2 times A3 times A4, and there's also two options. The first one is K equals 2, which results in A2 times A3 times A4. Okay, and the second is K equals 3, which means we first times A2 and A3 and then times the result with A4. So we need to refer to the M table for A3 times A4 and A2 times A3 for that we have known previously, and select the minimum value among these two options, and then store them into N24, right? And also S24 as well. Okay. So the results will be that in order to solve M24, we should let K be 3 because it has smaller costs. And we store the M24, which we store this value into the M24 cell. Okay, so after this iteration, we have solved all the subproblems of size 3. Okay, so what's left is just one problem, which is the original problem that we want to know, that we want to solve. Okay, so lastly, we want to solve the original problem of size 4. Okay, so the problem is like, I write it like A1 times A2 times A3 and times A4. Okay, so now we have 3 possible positions to place our K, to place our split. So K could be either K could be 1, or K could be 2, or K could be 3, and we want to choose the one option that gives us the minimal cost. Okay, so for K equals 1, we are actually doing A1 times brackets A2, A3, and A4. Okay, so it's actually M11 plus M24, right? So what is M24? It's the subproblem of size 3 that we already solved in the previous step, right? And plus the additional cost of P0 times P1 times P4. And for K equals 2, it is actually A1 times A2 into brackets times A3 and A4 with brackets. Okay, so it is a summation of M12 plus M3 4 plus P0, P2, and times P4. Okay, and these subproblems of size 2, they are already in our M table, in our N area. For K equals 3, it's A1, A2, A3 into brackets times A4, which is N13 plus 4 plus P0 minus P3 plus P4. Okay? So M13 is solved in our previous subproblem of size 3. Okay? So we did the same. We'll do the same thing and choose the minimum, choose the k that give us the minimum cost. And it turns out that the minimal k is 3. So and the minimum cost is 9,000. We put it here, and we put a 3 here. So now we have solved the problem. Okay. So our conclusion is that in order to solve the problem of A1 times A2 times A3 times A4 with these given dimensionalities, the optimal solution is 9,375 in terms of number of scalar multiplication. Okay. So what about the optimal way of doing the parentheses, right? We not just need the optimal solution, not just need the optimal cost, but also the optimal way of doing the parenthesization. This is what we care about more. Okay, so it's quite easy to achieve this goal to obtain to print the solution. Okay. So we just refer to the S array. Okay, so S array tells that where the k is in solve that particular subproblem, in that particular size of subproblem. Okay, so the S14 here, it's 3, right? So it basically says that in order to solve A1 times A2 times A3 times A4, we need to put the k here, right? We need to put A1 to A3 into the parentheses. Okay, so how do we further split A1 to A3? And it's easy because we just simply refer to the elements in S13, right? S13 is 1. It tells us that in order to solve it, we need to put a k here right after A1. Okay, and A2, A3 is just 2 matrices put together. Okay. But if you refer to the table, it tells you the information that it should be 2 because you are splitting A2 and A3. Okay, so now we know that the solution is put A2 and A3 into parentheses and group the results with A1 into parentheses and lastly times it with A4. And this is exactly the optimal way of doing the parenthesization for the inputs of A1 to A4. Okay, and we can easily write some helper procedures in order to split the optimal solutions. So it's a recursive way of doing so, given the S, which is already computed, and the I and J that refers to the starting index and the ending index of the subproblem. So you can print the information needed. You can print all the K's that are necessary, or you can print the so this procedure helps to print the the final results of parenthesization. So if I equals J, you just print that particular matrix, and in other cases you need to print the left parenthesis with right parenthesis, and in between you recursive call the subproblem. You recursive call the procedure onto the subproblem of small sizes. Okay, so Sij is actually the k, the optimal k to split the subproblem from I to j, and this Sij plus 1 is just k plus 1. Okay, so next we're gonna briefly go through the top-down method for this matrix chain subproblem. So this top-down problem, we'll provide the pseudocode for the procedure, but the thought is basically the same, very similar to the bottom-up method. So this top-down dynamic programming solution, it considers each table entry, Mij, as a solution, as a place to store the solution. It contains a special value to indicate whether it is solved or yet not solved, okay? And which is similar to the bottom-up way. So when the subproblem is encountered or is recognized by the procedure, it will first check. If it's first encountered, it will solve the solution and store it into Mij. And each time we say we meet the same subproblem again, then we simply look it up and return the value of that element in Mij cell. Okay, and we use this principle of solving a certain the same principle that we used before. So in order to solve the subproblem of from I to J, we need to use a K to iterate over all possible ways to do the split. Okay. So we'll need to use two procedures in this top-down method. First, we implement this memorized matrix chain procedure with inputs P, which is the dimensions of all matrices in it. So we will initialize the M array as a new table, and for each element in it for I from 1 to n and the j from I to n, we simply initialize the values to be infinity, and j from I to n because j must be greater than I. Okay, and then we call a second procedure called lookup chain with such parameters, with the m which we just initialized, and the p, and 1 and n. So this 1 and n indicates the span of the original problem. Starting index is 1 and ending index is n. Okay, so this is how the lookup chain method looks like. Okay, so it's a top-down method. So basically, given any inputs I and j, so if we want to solve the problem I and j, we will first check if that element Mij is already non-infinity. So if it's already a real value in it, so we just return it, which means we already solved it once. Then if not, we will continue executing all the code behind. Okay, so if I equals j, then it's a very primitive problem. We just put 0 into Mij. So in all the other cases, we need to solve the subproblem from I to j, use the principle. So from line 6, we use the principle of doing the split, right? We let k iterates from I to j minus 1, and we call the procedure itself recursively. Look at here. So we call the lookup chain recursively on the first segment or the first part of the subproblem that ranges from I to k, and the second part ranges from k plus 1 to j, plus the additional costs, right? So this pi minus 1 times pk times pj is the additional cost that we have been talking about over and again. Okay, so this is just the implementation of according to the principle here. We only record q when q is smaller than the previous value in Mij. Okay, and after these for loops, we'll return the solution as Mij. Okay, so next time when we encounter this subproblem npij again, we will find a non-infinity value in it. We can simply return it without solving it again. So that's the top-down implementation of this matrix chain uh, multiplication problem. So you will see that if we relate this to the rod cutting problem, we will find a lot of similarities in the code patterns. So the top-down method, like the top-down rod cutting method, it's also a rod cutting. It's also a recursive algorithm, but the bottom-ups ways of doing dynamic programming, we need to start from the smallest subproblems. And without recursive calling the procedure, we will need to arrange the subproblems in order so that we solve the smallest problem first. And so that later on, when we solve bigger ones, we can rely on these solutions to the smaller subproblems. All right, so that's so much for the top-down and bottom-up and top-down method for these matrix chain multiplication problems. So in the next lecture, we will sum up a bit on the dynamic programming topic, and if we have time, we will enter the next chapter for greedy method or greedy algorithms.